Right. Next, we discuss a concept called the density curve. Density curve looks like this. Right. If we look at this, this is the histogram we discussed in the last section. Right? And the density curve is a smooth fitting curve to the data. So we know this histogram is still like not smooth. If we smooth this part, we get this red line, and this is called the density curve. The density curve is a mathematical model of the distribution. So we use a mathematical formula to represent this. The density curve must satisfy a condition. The most important is the area under the curve above the x, the horizontal axis, must be equal to 1. So this part must be equal to 1. The area must be equal to 1. That's the first one. That is the requirement. All the properties, the area under the curve and above any range of values is the proportion of all observations that fall in that range. The meaning of this is the area under this curve here and above any range of value. For example, from 4 to 6, the range of value from 4 to 6. So this part from here, this part here, from 4 to 6, this area under this curve above this range from 4 to 6, this area is the proportion of all observations or data that falls in this range. So we know this distribution is applied to a lot of data. So what is the proportion of data that is between 4 and 6? This area gives us that number. If this one equals, for example, 20%, if this area equals 0.2, suppose if this one equals 0.2, then the number of data between 4 and 6 is 20% of the total data. So this is the meaning of the density curve. And if we understand this part here, the area under the curve above any range give us the proportion of the data, then this one absolutely correct, because under the curve here and above the horizontal axis must be equals 1. 1 equals 100%. So all the data must be within this range from the lowest to the maximum. So that is definitely correct. So this is a requirement. If for this distribution, from this histogram, and we simplify this to a density curve, we may have some density curve like this, we may have density curve like this, and we want to investigate the center of the density curve. The median of the density curve is the equal area point. That means if the median is here, then to the left, to the right, both area must be the same. So here, suppose this one is the median here, then the area for this part, this area here, this part will be equal to will be equal to the area from this median to the right. So that is the physical meaning for the median. For the mean of the density curve is the balanced point if made of solid material. that means is, for example, this one here, this is a definitely symmetric distribution. That means the median and the mean are identical. Here, left, right, both areas are the same. And also this is also the point of balance if this one is made of by a solid material, made of iron or wood or anything. Right? That means if we have hold this, then it will be balanced at this point. Here, for this skewed, right skewed distribution, the median is here. That means this area from here all the way to this point will be equal to the area from this median all the way to the right. The area must be the same. But the median here is if we made this one with a uniform solid material, then if we put this point at here, it will also be balanced. But if you put at this median point here, it won't be balanced. Right? So you can imagine if we put it at this point, right? Then if we put at this point here, then definitely this one will be like heavier. This one will turn clockwise. Right? So this is not a balanced point. Instead, the mean is the balanced point. So this is the physical meaning for the mean and the median of the density curve. There are a lot of density curves. The density curves are not necessarily to be like this, not necessarily to be like this. So actually, any curve, the lot of curves can be a density curve. For example, if we have like this, this one can be a density curve. And this one can also be a density curve. The only requirement is, we cannot say the only requirement. Okay, one requirement is this area must be equal to 1. And this area must be equal to 1. This is the condition 1. Condition 2 is the area under the curve above any range must be equal to the proportion of this theta. That means this density curve must be above the horizontal axis. We cannot have anything like this. We cannot have something like this. If like this, that means so this one here and this, so this area will be negative. So you can see, okay, some numbers from here to here, the proportion equals negative. This is not going to happen. So all the density curve must be above the the horizontal axis, and the area, the total area must be equal to 1. As we know, we have a lot of density curves, and we can only discuss the most typical, the most important, which is called normal curves. Right? Normal curves, also called Gaussian curve, Gaussian distribution. It is a symmetric unimodal. Unimodal means we have only one maximum. Right? So here must be like this. If you have something like this, right? So this one is not definitely is not normal distribution because we have bimodal. So one is here, another one is here. Right? So this one is not going to call them normal. Must be symmetric. Here, symmetric, must be unimodal, we have only one maximum, and must be bell-shaped like this. A normal curve is represented by a normal mu followed by parentheses, and inside which there are two numbers. The first one is mu, which is the mean. The second one is sigma, standard deviation. The standard deviation is represented by S. In the previous slide, but sometimes we use S, sometimes we use sigma. Both works. there's a little bit difference between this. Usually, for populations we use sigma. For samples we use S. Right now we do not need to distinguish this. And later in following chapters we are going to use, as we said. Okay, this represents the standard deviation of the population. This one S represents the standard deviation of a sample. Right now we don't need to distinguish this. We have n, mu, sigma, and we know mu is the mean, which means the center of the distribution. So the center is mu here, and this sigma is the standard deviation. The mathematical formula for any height of this density curve, for example, if I want to know this, what's the value I have here? So how high is this point? We know this is, suppose this is x. So this x, for example, equals x equals, we make some assumption. Okay, this equals 10. What is this, the value in the y-axis? That is fx is represented by 1 over sigma. Sigma is the standard deviation of the distribution, and square root of 2 pi. Pi is constant, because pi equals 3.14 and something. E here is 2.718, is also a constant, and negative half, and parentheses squared. That inside here is x, which is the required, the interest is x10, and mu again is the center, and sigma is the spread, is the standard deviation. So from here we can see x minus mu gives us the distance of this. Then divided by sigma means the size of this distance in terms of the standard deviation. So how many standard deviations this is. Then this square, then divided by a negative 2, then raised to the power of e, then divided by sigma, divided by square root of 2 times pi, then give us the height of this point. Usually we do not need to use this formula to calculate the height. Instead, we know for density curves, we are interested in the area under the curve above any range, not the absolute height of this density curve. But this gives us the definition for this normal curve. There are a lot of normal curves. They have looks like all are the same bell-shaped, but they may looks like some are very tall, some are very short, some are very thin, some are very wide. Okay? But we have some rules here. The first one is called 68, 95, and 99.7 rule. The meaning of this is in any normal distribution with a mean of mu and the standard deviation of sigma, then, for example, here, this is the mean. We know the standard deviation here equals sigma, the mean in this example equals 0. Within sigma of the mean mu, the mu is here. This one is sigma above the mean. This is sigma, 1 sigma below the mean. So within this range, the proportion of the data is 68% of the total. So this is called, this is the 68. Okay. The second one is, with respect to the mean, 2 standard deviation and negative 2 standard deviation within around the mean. So from the mean plus 2 sigma, from the mean minus 2 sigma, from here, this part, this area, start from here and all the way up to here, this all the way up to here, including this part. Right? So all this area will be equal to 0.95. And we know from the meaning of the density curve, that means the total data lies within this range is 95% of the total. The next is 99.7. It's very similar. It's 3 sigma plus mu plus minus 3 sigma. So from here to all the way here. So this is mu plus minus 3 sigma, and the data lying in this range is 99.7%. We can claim almost all data will be within this range. So this is the 68, 95, 99.7 rule. This rule is only a special case of calculation of normal curves. We know this for some, sometimes it's very convenient to know this, give us some approximation of data, of the data distribution or something, but usually we do not use this for calculation. For example, in the homework or in the test, I do not suggest you to use this one to calculate any normal distribution applications. Instead, we are going to use this goal concept, which will be discussed later after this, and also use the table for the calculation. We already know normal curve must satisfy that mathematical formula, fx equals something. And looks like there are several, very tall, very short, very wide, very narrow, they are different. Sometimes it's very convenient to transform all these normal distributions into one. It's called a standard normal distribution. We convert this or any normal distribution centered at mu and with sigma as standard deviation into a standard normal distribution. Still normal distribution, but the center equals 0, the standard deviation equals 1. For example, here, this is the data is given as a height, and we know the center equals 64.5 inch. And the standard deviation equals 2.5. So that is given like n 64.5 and 2.5. Standard deviation. This is a plus minus 1 standard deviation. This is 2. This is 3. And see, we can see this is normal distribution. And another one, this. We have all others, all different. But we want to convert any standard deviation, a normal distribution, into a standardized, like n, 0, and 1. So this is still normal. The mean equals 0. So here, this is the mean. And the standard deviation equals 1. So this is 1. This is 1 standard deviation. This is 2. This is 3. This is negative 1, negative 2, and negative 3 standard deviation. The reason is if we do this conversion, then all the calculations will be much similar, uniform. We can use table to do all the calculations. It's very convenient. To standardize a normal curves, we need to have a new concept. This new concept is called z-score. If we are given an arbitrary normal distribution, the mean equals mu, and the standard deviation is sigma. We want to convert this into a standard normal distribution represented by n, 0, and 1. We are going to calculate the z-score first. Z-score here, the standard value of x. This z-score is corresponding to a special x, the interested x. For example, here, the height of a young woman, and this distribution is for the height of a US young woman, are normal with mu equals 64.5 inches, and the standard deviation is equals 2.5 inches. And the formula for the z-score equals like this. This is the formula for the z-score. Z-score corresponding to x will be equal to that x value minus the mu, then divided by the standard deviation. This formula applied to this example, the corresponding this score to x will be equal to x minus 64.5, which is the mu, and divided by 2.5, which is the standard deviation of this distribution. Now we have several examples. The first one, if x equals 68 inches, then the corresponding z-score will be equal to plug this x into here, so 68 minus 64.5, then divided by 2.5. Okay, that is z-score equals 1.4. Corresponding to x equals 60 inches, x equals 60, we plug this 60 into here, 60 minus this will be give us a negative number, negative 4.5, then divide by this one, then the corresponding z-score will be negative 1.8. So this is how we calculate the z-scores. Later time we are going to learn how to use this. What's the purpose for this z-score? How to use z-score to calculate the proportions or probabilities later time. We just mentioned for any density curve, the area under the curve, for example here, under this curve, and above any range, give us the proportion of the data within this range. This is always true. Now there's another concept, it's called cumulative proportion. Cumulative proportion is the proportion of observations in a distribution that lie at or below a given value. For example here, this x may be equal, number for example equals 10 or equals any number here. What is the proportion of data in this distribution that lies at and below this x value, which equals 10. That proportion is the area from here all the way to the left of the normal curve. In this part, this is the yellow area. So the area of this yellow from all the way to the negative infinity, right? Okay, so this negative infinity all the way to x here, this and this curve, this area gives us the cumulative proportion of x. Now we want to know this cumulative proportion. So how to calculate this proportion? For example, if x equals 10, what is this area? From math, we know the area actually is the integral of this curve from somewhere to somewhere, but we do not want to use this. The good news is for any standard normal distribution, we have a table at the back of the textbook which calls table A, and we can easily calculate the area. We don't need to do the integration. We use this table A to look up the area. Right? And the table A at the back of the textbook is given like this. Okay, so here, and here we show how to use this table. This table has some portions. Z is the z-score here. And on the left-hand side, we have some numbers, the leftmost column. And on the top, we have some numbers. All this column and this row combined together give us the z value. For example, if z equals negative 2.4, okay, negative is not see this. I'll give you another example. Suppose z equals negative 2.4, right? So z equals negative 2.4 is here, 2.40, right? 2.4 is here, 0, this 0 is from here. So this is the cumulative proportion for corresponding to z-score equals negative 2.4. Right? And another one is, for example, how about the negative 2.45? Right? Negative 2.45. Negative 2.4 is here. This is 4, 0, 1, 2, 3, 4, 5 is here. So this number corresponding to negative 2.45. Right? And this number is corresponding to z equals negative 2.46. So for this table, we can only check z table with 3 digits, right? Negative something, then up to the 2 digits after the decimals. Right? And this one is from negative 3.4 all the way up to 0, right? And we have table. This is called the table A. Now, what are the numbers in the middle part? Those are the cumulative proportions. Right? And we have an example here to show that later time we use the example to show how to use this. Right? Okay, next one is we discuss how to do this normal distribution calculations. Right? If in this here, this example is very simple. If I want to know what is the cumulative proportion of the data that's less than or equal to x, so we just check this table A, so from negative infinity all the way to here. How about if I want to know the proportion of data that's above 820? Above 820 means all the way from here, all the way to the maximum. We want to know this area. How to calculate this? Because in table A only give us the area from negative infinity, from the smallest number to this part. The value in the middle, in this part, give us the area to the left, from this x to the left, not to the right. If we want to know the proportion, the area or the proportion from this point to the left, to the right, how to do this? We remember that the total area of this curve and the density curve equals 1. So if we know this, then we use 1 minus this, give us the area of this. So this, if we want to find the area of this, we just use this total minus this part. Right? So this blue part equals the total minus this one, and this one equals 1. Right? Total area equals 1. That's the definition of density curve. And this part can will be given from the table. Right? So corresponding to 820, then we find the cumulative proportion from here. So we use 1 minus this one, then we get to the proportion for that. So if we want to calculate a problem like this, we use 1 minus this. Another example is I want to know what is the proportion of data that between 720 and 820. That means I want to know the area between 720 to here. I want to know this area. How to do this? Again, this one will be equal to this area from all the way to the left to 820, then minus the area all the way from the left to the 720. So that means this one is this big area from here to the left. So this one here to the left, then minus from here to the left. So give us the area, this part, which is which we are interested in. Right? So the area left to 820 in this example equals 16%, and the area to the left equals 7%. Then we subtract these two numbers, we get the area which is equals 9% for this one. Right? So we need to understand the ideas of this and this, because in table A the proportion only give us the cumulative proportion. That means from negative infinity, from all the way to the left to the interested x. Now we know the concept of this goal. We know how to use table A, and we also know how to calculate some special problems like this one and this one. Both are not given directly from the table A, and now we can calculate a real problem. Right? So here is a normal distribution calculation example. Right? This is important, so everybody is supposed to understand this. The question is given like this: the SAT scores are normal distribution, and correct or not, this is given. Right? Normal distribution like this. So the mean equals 1026. The standard deviation is equals 209. How many students are in the range of 720 to 820? So how many students their scores are within this range? Right? So this one actually is illustrated by this one, from 720 to this one. This one is the SAT score normal distribution. Right? So here, how we do this? As we know, the table A here, if you look at this, on this side and on the top, these are the z-scores, not x. So we need to calculate the z-score first. And this z-score, the formula is x minus the mean divided by the standard deviation. So we need to memorize all these formulas. So here, we need to calculate two z-scores. The first one corresponding to this, the second one corresponding to this. So this is x, this is also x. We need to calculate the corresponding z-scores. So x is within this range and this range, greater than or equal to 720 and less than or equal to 820. Then this x, will be changed into a z-score here, and this 820 will be changed into this corresponding z-score. The z-score equals x here, 820 minus the mean. The mean is here. Then divided by standard deviation. Standard deviation, which equals this. Right? So all these numbers are given. So corresponding to 820, that z-score is this. Similarly, corresponding to 720, the z-score is x 720 minus mu, then divided by standard deviation. And this value is negative 1.46. And this value equals negative 0.99. Corresponding to 720, the z-score equals this. Corresponding to 820, the z-score equals this. So now we can plot the normalized, standardized normal distribution. Right? The original normal distribution look like this. Right? The mean equals 1026, and this one equals 820. This one equals 720. We want to know, right? So this is the proportion we want to know. And after the standardization, right, the normal distribution will change into here. Look like this. So this mean here. Okay, that's it's not very good. Okay, I suppose the line. Okay, so let me erase this. Erase this. Okay. This. Okay, anyway, this is good here. Okay, so here this must be like this, right? So now after the standardization, the mean will change from 1026 into 0, and the standard deviation will change from 209 into 1. So this is one standard deviation, some here, this one. And this score 820, we are changing it to negative 0.99 is okay. Is around this point, and this 720 is around negative 1.46. So it's here. Oh, it's gone. But anyway, still looks like the same thing here. But the good news is this area can be calculated from the table A. We just need to use this score here, and we know if we want to calculate the proportion here, we need to calculate the area, this part, then minus the area, this part, then the difference between these two will be here. From table A corresponding to negative 0.99, this is this one. Right? How to get this number? You go to table A here, negative 0.99. This is not very clear, but you know how to get this one. Then 0.99, then you find that value equals somewhere around here. So that equals 16%. Right? So this one. Then corresponding to this, this value is equals 7%. So again, negative 1.46. You go to table A here, negative 1.4 somewhere here. Then you find this one equals 7%. Okay, maybe equals somewhere here. Now we subtract these two, we get the difference, which equals 9%. And 9% is the proportion of data whose this score is between this and this. So that is the direct explanation. Or back to this original question, this 9% is the proportion of students whose SAT score are from 720 to 820. So now you can see this is the beauty of standardization. Instead of directly calculate 720, 820, we deal with these scores and we use table A to calculate all these proportions. Okay, so this is the calculation of normal distribution. Then next, it will be also deal with normal distribution, but the inverse problem. So inverse problem, we have some practical application. For example, here, suppose the SAT score satisfy normal distribution. This, so satisfy this. The mean equals 505. The standard deviation equals 110. If you want to be on the top 10, you want to be top 10, what score should you get? So this is an inverse normal inverse problem. The normal problem is if you get a score of something, then what is your proportion or what's your position? Top 10 or top 5. Here is you want to be on top 10. So what score should you get? So like here, still normal distribution, and this part is your score. So we want to know what X you should get. And you want to be a top 10, that means this area, this proportion equals 10%. Again, recall table A, cumulative distribution. The numbers in table A is the cumulative distribution, means the area from this point all the way to the left. So in this example, you want to be top 10. So only 10% will be higher than you. That means you are higher than 90% of the student. So the number must be equal to 0.9. So we check table A. We cannot check 0.1 from the middle. We need to check 0.9. That means, so here, table A, we need to find 0.9 from this part. Not 0.1, the physical meaning, keep in mind. This is here. this is equal 0.1. So we are looking for this part. So this part equals 0.9. All these numbers in table A give us the area from negative infinity all the way to somewhere here, to the left. Okay? Another thing I want to mention is this is our table A. Right? In the online or in other textbooks, they may give us different. They may say, okay, this is the area, or this is the cumulative proportion given in the table. So if you look at our textbook on the top here, okay, our represented by this. So this part, that means these numbers are given the cumulative proportion to the left. Some table may give us to the right. So if you use different tables, not the table not from our textbook, you need to make sure understand this. Right? So otherwise you're going to make a mistake. Right? So in our textbook we use this one. So all this one is the area from X all the way to the left. Right? So we already understand that we need to check 0.9. When you look at the table A, 0.9, the corresponding z-score equals 1.28. Right? 1.28, that means you find 0.9 from somewhere, then you read this z-score here, and that part add up together. Right? And in this example, it says the result equals 1.8. So from X, from this 0.9, we check table A inversely, and we find z-score, the corresponding z-score must be equals 1.28. To satisfy this 90% below you, or you will be on the top 10%. Okay, now this, we know the z-score here, and we know the z-score, so this score is calculated by x minus mu over standard deviation. And we know the mu equals 505, we know the standard deviation equals 110, and we know the z-score equals 1.8. What we are looking for is this x. So this x is easy, right? X equals z times standard sigma, then plus mu. So x equals mu plus z-score times sigma. So in this example, it equals 645.8. So that means if you can obtain 645 points, then you will be in top 10. So in general, for unstandardizing, we are looking for x from something, so from the z-score. So x will be mu plus z times standard deviation. So we are going to stop here, and the most important in this section is the normal distribution. We need to know the concept of z-score. I know you need some time to consider this, and also how to use the table A, and also calculate the inverse problems. Okay, thanks. Normal distribution is very important. We need to know how to calculate problems with related to normal distribution, and also inverse problems. Here we are going to discuss more examples, because we are going to use this concept in the following chapters a lot of times. I want to make sure everybody understand and feel very comfortable doing this kind of problem. We discussed several examples. I just randomly give you some examples and show you how to do this step by step. And I want you to follow the correct steps to do the homework and the test. Example 1. We assume a data set satisfies normal distribution, and the normal distribution is given by two numbers. The first one is the mean. Suppose the mean equals 1,000, and there's a second one is called the standard deviation. And suppose the standard deviation equals 200. And if we draw the picture, it looks like this. The mean here is 1,000, and the standard deviation is 200. So this is 200, and this is 200, 200, and so on. what I want is, for example, if I want to find the proportion of this, suppose this variable is represented by x, and I want to know what is the proportion represented by p that data x is less than, for example, 800. Right? What's the less than or equal to doesn't matter, right? The reason is, okay, let's discuss this. What's the probability that x equals 800? We know that the probability is corresponding to the area under the curve and above any range. The range here is from 800 to 800. So that means if we draw a rectangle, the height is this, the width will be equals from 800 to 800, which equals 0. So that rectangle has 0 width. That means the area equals 0. So the proportion for a particular data exactly equals 800 will be equal to 0. Right? Because the area equals 0. So this. So that's why it's less than 800 or less than or equal to 800, we have the same result. What I want is, in this example, I want to know the probability or the proportion in this chapter that a data is less than or equal to 800. So what is this? That is our question. Solution. Step 1 is we need to find the z-score corresponding to this. That means we need to convert this normal distribution into standardized normal distribution. So the normal distribution, I'll draw this just for easy to understand. So here, and this one will be equal to 0. This is the mean corresponding to 1000 will be equal to 0. And this standard deviation, this one, the length here will be equals 1. This one will be equals 1. So this equals 1, this one is negative 1 here. The step 1 is to calculate the z-score. So z-score for x equals 800. For x equals 800. Okay, let me move this down a little bit. Solution, x equals 800, so z-score equals, I want you to write the formula first. The z-score equals x minus mu, then divided by standard deviation. So here we can say, for normal distribution, mu equals 1000, and sigma equals 200. This one equals 1000, this one equals 200. So I want you to list this to make clear. So z equals this, then we plug into numbers 1000 minus mu equals, x equals 800. So mu x equals 800 minus 1000 and divided by this standard deviation, which equals 200. So this one will be equals negative 1. Right? Then check table A. So for z equals this, so the probability x less than or equal to 800 equals, this is the original normal distribution, and after the conversion we have a standardized normal distribution that equals p, the proportion of z less than or equal to negative 1 here. The next step is to try to find the table A, and I don't have the table A here. Let me see if the table A. Right, table A. For x equals, the table A looks like this. This is the z-score here, and for z equals -1, and the -1, the result give us 0.1587, and this part equals 0. This one is somewhere equal -1, and this value is equals 0.1587. And keep in mind, above our table, okay, this value, the value is given in this table corresponding to the proportion from this point to all the way to the left. So that means we are looking for x less than this, or corresponding to z less than -1. That is exactly this area. Right? So the result here will be exactly that what we want. So that's all. So that's the end of the solution. Right? So this is the first one, and we find. I'll give you another one. All this together. Right. We have another example. Example 2. Again, we are given a distribution, it's normal, and we assume the mean equals equals any number. Equals we can use for example, if this is for the suppose the data is for the midterm test, right? The mean of the class, suppose the data set satisfy a normal distribution, although yours is not, but we assume this satisfy normal distribution. Suppose the mean equals 75, and the standard deviation equals mu equals 75, and the standard deviation equals let me see, suppose equals 5, like this. And usually, if it's normal distribution, this class must be very large. Right? Anyway, we just assume this is correct. Then what I want is the proportion of a student in percentage that their score, again, we said the score of x is, let's see, pass the test. Pass the test means greater than 60. So that is what we want. So how many of the students will pass the test? If we draw this picture here, this is you don't need to draw this in the homework, but if you draw this, it will help us understand. So this here, this one equals 75, and again the standard deviation, this one equals 5. So this part, this equals 5, and this one equals 5. The first step 1 is to standardize the problem. That means to try to find the z-score. And we correspondingly to draw the standardized distribution here. It will be not good, but so this is equals 0, and this one equals -1, this one equals -2. Sorry, this is positive 1. And 60, 75, this is 5, maybe something here, so 60 is around here. We want to know how many will pass the test. Pass the test means the score is higher than 60. So the area from here to the right is what we are looking for. So x is less than, is greater or equal to 60. We need to find the z-score corresponding to 60 somewhere here. This is the z-score here. Then we can just check table A, try to find the area for this part. This is what we are looking for. But keep in mind again, in the table A, the number checked from the table give us the area to the left. So we are going to have a special treatment to do this. Alright, anyway, first one, solution, and we follow the steps. Again, mu equals 75, and 6 standard deviation equals 5. You copy all this. Then we know x equals, the interest is the x equals 60. And the next one, try to find the z-score. We write the formula first. So z equals x minus mu divided by standard deviation. And this one will be equal to plug into numbers 60 minus 75 and divided by 5. So that one will be equal to negative 15, so negative 3. Now the proportion of x, so here is z-score. So z less than or equal to negative 3. This one, keep in mind, this one is not what we're looking for, but this one number is given in the table. So this one from table A, we look at the table corresponding to, again, we emphasize how to use table A. So this one here, this is z, and we have some part here, so negative 3.4, negative 3.3, and some 0, 0, 0. 0, 1, and so on, all this. This one is negative 3, so negative 3 is somewhere here, negative 3.0. And we just look for this number. The number here is 0.0013. So this equal to 0.0013. We cannot stop here because this one gives us the proportion that less than negative 3 or correspondingly x less than 60. What we want is x is greater than 60. So we just write this x greater than or equal to 60. That is what we are looking for. Will be equal to the proportion of z greater or equal to negative 3. And this one will be equal to 1 minus the proportion z less than or equal to negative 3. So that will be equal to 1 minus, this one is given from here, so 0.0013. So that's give us 0.9987. So that equals 99.7%. So that is the second problem. Hopefully this gives you the ideas how to solve this kind of problem. I do not want you use any, for example, software or calculators, just plug into the numbers, then just give me this number. What I want you is you should understand the problem, understand the concept of normal distribution, and know how to calculate this. The reason is based on my experience, some students before just use a calculator maybe to punch in the numbers, give me only the result. Okay, it says 99.87%. But if I give you some other more complicated problems, he cannot just plug into numbers into the calculator, then he can do nothing. So that is not what we want. I want you to understand the concept first and know how to solve the problem. Right? So this is the second example. Both example 1 and example 2 are normal distribution. Next one we are going to discuss 1 or 2 for inverse normal calculations. Example 3, so inverse normal distribution. Let me make another one. Suppose again, normal distribution, the mean equals 500, standard deviation equals 10, suppose. And if we draw the picture, it looks like this. So this is the mean here, 500, and the standard deviation here, this one here. So both part equals 10 standard deviation. If you want to be, for example, in the bottom, let me see, 10%. So this one here, you want to be the bottom 10%. What, again, this variable is represented by x. What is the x you should be for this requirement? I want the probability for x less than or equal to something, so this one equals 10%. We are looking for what the x is. Again, we need to normalize the problem, right? So this is always the step 1 or step 0, right? We draw a standardized normal distribution, like here, and we know this is always equal to 0. The reason is corresponding to the mean, the z-score must be equal to 0. The reason is very simple, because z-score equals x minus mu divided by standard deviation. So if x equals the mean, then this one always equal to 0. That means corresponding to the mean, the z-score is always equal to 0. So this is z. So this is always true. From table A, we know here this one equals 0.1, equals 10%. And this is the proportion from the sum point from here, which we are looking for all the way to the left. And from the understanding of table A, we know this number, 0.1, is exactly the number from the table. So the table looks like this, z-score here, z here, and the numbers in the center, this one is exactly give us the area from this point all the way to the left. And so somewhere there must be a 0.1. We are looking for this 0.1, then once we find this, we look for the corresponding z-score here and here. We add this number and this number together, this gives us the z-score. Once we know the z-score, use the inverse formula, we can find the corresponding x. Okay, so now we look at the table A, try to find the z-score. The table A, we are going to find 0.10%. The 10% is, let me see, where is it? Right, 10% looks to me, it is somewhere, the 10% is somewhere here. This number here equals 0.1003, about 0.1003. So that's numbers here. That's very close to. This is the closest to the 10%. Alright, so as we find this one, I go to this way, find the corresponding number here, that will be equal to negative 1.2. So this is negative 1.2 here. Negative 1.2. And we need to find this number also on the top to make this more accurate. And this number here is 0.08. So this number here is 0.08. So we need to add these two together. And this is negative number, so this is also a negative number. So we, okay, let's write the solution. For proportion z, we can write it like this. For a proportion of 10% from table A, the z-score equals negative 1.28. Negative 1.28 here. Then as we know, because z equals x minus mu over sigma, and we have x will be equal to mu plus z times sigma, and then this one will be equals mu, here we write again, mu equals 500 and sigma equals 10. So this one equals 500 plus z equals negative 1.2, so negative 1.28, and times sigma equals 10 times 10. So this is going to give us this is negative 12, so that looks like 487.2. Right? So 487.2. Right? Then that's the solution. Because we are looking for what is x is, so this proportion will be equals 10%. That's it. Now we discuss another one. Maybe a little bit more complicated, but let's try. Example 4. Again, a normal distribution. We still use the same example, right? 500 and the standard deviation equals 10. And if you want to be in the middle, for example, 80%, want to be in the middle, let me see, 60%. All right, let's write 50%. Right in the middle, 50%. Then what the data? What is the data? So this one. The question is like this: we have a normal distribution, and the mean equals 500. The standard deviation equals 10 here, equals 10. So this one gives us 20, right? From negative 10 to positive 10. What we want is, if you want to be right in the middle, 50%. So 50% is suppose somewhere here. So maybe here, right in the middle, this one here. Okay. You want to be in the middle 50%. So this one is 50%, around the mean. What we are looking for is what the data supposed to be. So we can see that the data must be arranged, right, from somewhere here to somewhere here. So we are just looking for these two numbers. That's the problem. Again, we need to standardize the normal distribution. The standardized normal distribution. Looks like this, and this one will be equal to 0. Now we are looking for 50% here. So we need to find the z-score here, z-score 1, and z-score 2 here. So once we find the z-score, we can calculate the data. Suppose the data are x. So this one here, and this one here. We need to know what this z-score is, this z-score is. From the inverse formula, we can find the x. Try to find the z-score. That means we need to know this proportion. Right? Keep in mind, this is a density curve. So the whole area under the curve above the horizontal axis is 100%. and this part equals 50%. And it will be, this is also symmetric. So 50%, that means this one is 25%. Then this one here will be 25%. So that means the area for this part will be equal to 0.25. 0.25. Oh, no. 0.25. So this equals 0.25, then this one will be 0.25, then these two add up together equals 50%, that leaving us in the middle 50%. So that is what we want. Right. So now that's easier, so we just look at the table A, from the middle, from the center, try to find this 0.25, then we can locate that z-score. Right. Now I'm looking at my table A, 0.25, 25%. 25% is I found two that are around the 25. The first one is 25. So I found two numbers here. That's equal 0.2. This number is 0.2514. And another number is 0.2483. 0.2483. And all this line here corresponding to negative 0.6. And this one on the top corresponding to 0.07. So 0.07. And this one corresponding to 0.08. If you look at the 0.25, it's almost right in the middle, right? Right in the middle, so we can use a technique called the interpolation, which will be discussed a later time, but you can just think, okay, this is, the value is right in the middle, so this z-score must be right in the middle, right? So we are going to set the z-score equals 0.6, and there's another 7.5 here. So I write, okay, so I remove this. I put in here, so negative 0.6. The solution. Solution, we can write first line. So the mean, mu equals 500, and the standard deviation equals 10. And the proportion for x will be equal to, we can write x equals x1 as the first one. So x equals x1, so less than x equals 1, less than or equal to x1 equals, we know this one equals 25%, right? So 25%. So from the table A, for this proportion, of 0.25, the z-score, z1, corresponding to this one, z1 here, will be equals negative 0.6, and we said we use the middle number here, so 7.5. Then use the inverse, the formula, so the x1 will be equal to the mu plus z times z1 times sigma. So that one equals 500 plus this one equals negative number, so minus 0.7 and times sigma equals 10. So that is 6 points. So let's see, it was 493.25. So that gives the x here. We cannot solve at this point because we are going for a data range. The lower x equals this one. So how about the x2? The x2, because they are symmetric, we know this value equals this width equals this width. This one is negative, this part, then this value must be x plus, this must be the mean plus this part. So we can directly write this part. We can directly write this. It's not easy to write now. How to remove this? Okay, x2 equals the mu, and from the symmetric property, we know this corresponding to this score must be a positive this number. Right? So we mu plus z2 sigma, it will be equals 500, equals 500, then plus 0.675 times 10, so that will give us 506.75. So this gives us the range. Right? The range is from here to here. Okay, this is the example 4. We can discuss more examples. For example, if I tell you the x value and also the proportion, and I tell you that this is normal distribution, I know the mean, but I want you to find the standard deviation. Okay? You can still play with all these formulas from table A, from this z-score formula, and also the probability, the proportion, try to find the sigma. Or if you know the sigma, you can find the mean. So no matter what. In this problem, we have several variables. If we know all others, we can find the other one. Okay, so I think that's good enough. Okay, thanks.